Hello everyone! Today we're going to be going over analyzing lines of fit. So our goal today is to be able to collect and use data to analyze scatter plots to determine patterns, describe relationships, and use graphing technology to determine regression lines. So first up, let's talk about residuals. Last section I talked about how a line of best fit, when you do it properly, there should be the same amount of data points above as below. Well, those data points are actually the distance between them is the residual. And a residual can have a positive or negative value or be zero, meaning it's exactly on the line. And a scatter plot of the residual shows how well the model fits the data set. If it's a good fit, the absolute values of the residuals are relatively small, and the residual points will be more likely evenly dispersed about the horizontal axis. So it should be closer to like a horizontal line or closer to the x-axis. If the model's not a good fit, the residual points will form some kind of pattern that suggests the data points are not linear. Wildly scattered residual points suggest that the data might have no correlation. So we're going to be able to look at the residuals here in a moment. So we're going to take a look at our equation, y equals negative 2x plus 20, and see if it models the data in the table shown. So we can see here in the table shown that we're going to look at the week x, and it increases by 1, and our sales in millions y, and we can see that there is a decreasing pattern. So it lets us know that our slope should actually be negative, which in our case it is. So that's a good start. So we're going to fill out this table here on the right. Our x values we're just going to take from our table, so we just have to label it 1 through 8. And understand that this process that we're about to do is very tedious and it does take a little bit. And our y's we're going to take from our table as well. And remember, our y's are actually representing millions of dollars, not just like $11. And then we're asked about the y value from the model. That means our equation is the model. So we're going to take our equation, which is negative 2, and we're going to replace the x with our x value from the table. And we're going to get negative 2 plus 20 is 18. And we need to fill out our y value. So it's going to take multiple rounds of this. So essentially we're going to do this 8 different times. I personally will write the equation step by step, one by one when doing this process. But I need to remember that when I'm filling out where the x variable goes and replacing it, I need to change those numbers. So again, just filling out the information to be able to show us where the information comes from, so it makes sense. And now we can finish solving our y values. So our next line will give us negative 4 plus 20 is 16. Negative 6 plus 20 is 14. And I can see that we're actually having a pattern where it's going down by 2's. So as I go through this, I can just show subtraction by 2 because that is what the pattern is showing us. And you can double check the math to make sure. Now the residual is where you take your y value from the table and you subtract it from the y value from the model. And we'll tell you how far the residual is. In our first case, it is 1. And it is okay for it to be negative, as previously stated. So we are going to do this for every single data point for our residual. And again, this is our tedious process. It takes some time. Continuing, and it is okay to also get 0 as previously mentioned. I messed one up. 1 second here. 7 minus 6 is not 0, it is actually 1. My bad on that. So now what we're going to do is make a scatter plot from the residuals. So my x-axis, I'm going to label 1 through 7 because I do not have enough lines on this scatter plot graph, unfortunately. And on my y-axis, I'm actually going to use the residuals. And I know it's between 0, or actually -1 and 1. So I don't have to label it far. This gives us a heads up that this might be closer to a horizontal line because the residuals are not varying very differently. They're actually fairly close. And once we graph them, my first point will be 1, 1. I'll look at my x value, then my residual, 2, -1, 3, -1, 4, -1, 5, 0, 6, 0, 7, 1. And if I was to graph the last one, it would be 8, 1. So we look at our scatter plot. It looks like it's fairly close to the horizontal, or x or y equals 0. So based on the scatter plot, what do we notice? The points are close to the horizontal axis. Which means that the model is a good fit. So now we're going to take a look at another table. In this table, we're going to be modeling with temperature and the number of weeks. So this table shows the high temperature on Monday for 8 weeks, and the equation y equals 7x minus 8 models this data. So we're going to see if the model is a good fit. So first we're going to fill out our table for our x and y values. And I can tell you right now, just looking at this table, it looks like an Oklahoma spring, or possibly in those times where we have random warm points in the winter. And just from experience, I can already tell our equation is not going to model the data, simply because if we put our week 50 in, it would be a huge number. So we're going to look at our y value from model. So we're going to take the equation, and again, we're going to begin the process of writing this equation over and over again. Again, this is where the tedious part comes from. But remember to replace your x value from our table or graph. It should not be the same number. And then we just complete this equation over and over again. Don't forget to leave yourself enough room to fill this out. And then we can solve. 7 minus 8 is -1. 14 minus 8 is 6. 21 minus 8 should be 13. And I'm already discovering a pattern here where it looks like it's increasing by 7. So I can go ahead and continue to fill in my table. You can always double check the math. But now let's calculate our residuals. Again, it is going to be our y value minus our y value from model. And then the first one we get 49. And then we're going to get 37. And just by looking at this, I can tell that this is not going to be as nice as our previous one. This one we can see that our residuals are actually much larger numbers. And as we graph them, we're going to see that they are not close to the horizontal axis. That should be 18 there. 56 minus 34 should be 20. Ooh, excuse me. Should be 22. 67 minus 41. And our very last one. A calculator here is always very useful. So now, once we fill out that table, we need to graph it. Again, unfortunately, my graph does not have 8 points, so I'm only going to use 7. That was my bad. But here we can look at our residuals and see that it varies from our largest number, 49, to our smaller number, 18. So I am just going to go up by, let's see here, I got 1, 2, 3, 4, 5, 6, 7. If I go up by 5s, my limit is 35. So I'm going to go up by 10s. So my first point, x, is 1. My residual is 49. So I'm going to graph that. And this is a lot of approximation. Our next point is 2, 37. Let's say it's between 30 and 40, closer to 40. 3, 29. Between 20 and 30, closer to 30. And I'm taking, as I'm doing this, I'm watching my graph. I'm seeing how this scatter plot is reacting. So I can kind of see what kind of interpretation I'm going to have here. Right now it looks like I have a negative correlation just on the scatter plot on the residuals. But I know on my next point, 622, it's going to change because now it's going to start going up. So it looks like it has a minimum on our scatter plot, and it's going to go back up. So this right now looks more like a U or V shape. So this model, the scatter plot is not a horizontal line. Or is not on the horizontal axis. So this means that the equation does not model the data. So we were able to take a look with our residuals to see if equations that model the data would be a proper line of fit. Our first example did not show it to be a proper line of fit, but we can see what's coming up. So some general vocabulary is a linear regression is used to predict the value of a variable based on the value of another variable. A line of best fit is a straight line that minimizes the distance between it and some data. And a correlation coefficient, which we're really going to be using next, is a number between -1 and 1 that tells you the strength of a relationship between variables. Generally, its symbol is R. So let's take a look here. We can see in our little chart here that when R is -1, it shows a strong negative correlation. When R is 0, there is no correlation. And when R is 1, there is a strong positive correlation. If you make note here, it is saying that there are some notes on how to use a TI-30XS graphing calculator to be able to do the next part. And I will add those notes in. I am going to actually be using Desmos to help me out. So what I'm going to do is take this information and go to desmos.com, and I have it pulled up over here. And I'm going to click on the 3 lines in the upper right and scroll down until I can find statistics, linear regressions, so I can open it. Because in Desmos, this gives us a lot of information. What we need to do is fill out our table here over and over again with our actual information from the graph. Oops, I need to undo that. Let's see here. So just filling out this graph. And you can see how the line is changing consistently as I input new data. So again, I'm just putting in my X variables first. And it's always good to double check your data, especially when you're using the calculator, because it is so easy to mess up. Always double check your data points. And the reason you see me typing this so quickly is I took a picture of this through my phone. So that way I would have a quicker way to look between Desmos and my actual chart. Sometimes multiple uses of technology can be very beneficial. So we are actually looking at the table that shows the number of teachers and the number of students of several different schools. So we are actually going to look at a student to teacher ratio. And here we're given some information. We have our equation y equals mx plus b. They give us our value m, and they give us our value b. So we have our slope and our y-intercept. And Desmos also gives us our R value, our correlation coefficient. So let's take a look at our questions now that we use that to fill in and make equations. It's asking us to use a graphing calculator to find an equation of the line of best fit. In this case, we are going to want to use it to the nearest integer. So taking a look here, my slope is 20.6. Rounded, that means my slope will be 21. So y equals 21x plus, we take a look here, and our y-intercept is 42.3. So round it to the nearest integer, it will be 42. And B, it is asking us to identify and interpret the correlation coefficient. So going back to Desmos, we look for our R value. Our R value is 0.959. I like to round this to the nearest thousandth. So that will give us actually a correlation coefficient of 0.960. And if I look at my graph above, the closer it is to 1, the stronger it has a positive correlation. And since we're really close to 1, we have a strong positive correlation. The next one we have is interpret the slope and y-intercept. The slope, it actually tells us our student to teacher ratio. So that means we have 21 students per 1 teacher. And our y-intercept, again, we are going to make x be 0, meaning there are no teachers. That would mean there are 42 students running a school with no teachers, which would never happen. So the y-intercept in this case has no information given. It is not needed. So it does not have any useful information because it does not work in this case. So we're going to do some interpolation and some extrapolation from this information given. So we're going to be able to, with interpolation, being able to use a graph or its equation to approximate a value between two known values. And extrapolation is when we use a graph to predict values. So interpolations, we do some introspection to approximate what we need to do. And some extrapolation is we're going to be able to do some extra work to predict what's coming up. So in part A, it's asking us to refer to a prior problem for this example, the one right above us. And we're going to use a line of best fit for this example. So y equals 21x plus 42. And it's asking us to approximate the number of teachers when there are 336 students. This lets us know we're going to do some interpolation. If I look here, I see I have 336 students, and students is our y variable. So I am going to substitute in 336 for y to be able to solve for x. So we would just need to subtract 42 on both sides and then divide everything by 21. And I'm going to be doing that on a calculator off screen. So that way I can get the information and see that when there are 336 students, there should be 14 teachers. I misspelled that. And in B, it is asking us to predict the number of students when there are 20 teachers. So we're going to do some extrapolation to predict. And teachers is our x variable, so we need to substitute in for x. And in this case, we're going to have 20. So we're going to see how many students there would be using our line of best fit equation if there were 20 teachers. And we're going to get, again, using a calculator off screen, we're going to get that there are 462 students when there are 20 teachers. We're going to be almost done with this. We got one small area to talk about, correlation and causation. So a correlation is a mutual relationship or connection between two or more things. And a causation is when a change in one variable causes a change in another. So we're going to first take a look at correlation in parts A and B, because it's asking us to tell whether a correlation is likely, and if so, tell if there is a causational relationship. So first we got to see if there's a correlation. And in part A, it's saying time spent babysitting and the amount of money earned. So we ask ourselves, if we spend more time babysitting, do we earn more money? In this case, yes. So there is a correlation. And not only is there a correlation, there is a positive correlation. A negative correlation would be if you work more hours, you'll earn less money, which does not sound like a very good thing. So since there is a correlation, we're going to see if there is a causal relationship. So we're going to see if we change one variable, does it cause a change in another? So if we say that we work less hours, what does that mean for our money? Well, if we work less hours, that means we earn less money. So there is a causal relationship. And in B, it's saying eating organic food and getting a good score on a test. So eating a good breakfast is really good to help improve test scores, but eating organic food does not necessarily relate to getting a good score on a test. So that means there is honestly no correlation. Which means that since we don't have a correlation, we do not need to see if there is a causal relation. So from here, we are done with today's notes. Thank you for being here today.